Hel- Hello, can you hear me?
Yes, we can hear you. So maybe we can just take it away so we can get lunch or dinner, depending on your time zone. Let's go and tell us about causal modifications of gravity.
Yes, hi, it's a pleasure to be here. I'm going to be speaking about work done actually with a lot of the collaborators. So let me start with like the general question we're trying to answer. So okay, we're all familiar that Einstein gravity works very well, and we're going to try to ask, like, if we assume that the world is causal unitary, well, no, we don't know that's the case, but if we assume that, how different could it be? How much can you modify Einstein gravity without messing up with these more basic things? Okay, that's the general question. More precisely, I'm going to introduce the setup in this buzzy slide. So we have a picture on the world that's the setup we imagine that, okay, with the standard model, the physics we're probing at colliders, and the key scale today will be the mass here of higher spin particles, meaning like particles with spin 4 higher. And the idea is we want to see if there are no spin 4 particles before this mass, we want to see how different could theory be from GR. Okay, so we're looking for the biggest possible effects. Notice that this is exactly the opposite as the previous talk, which was trying to see how close to Einstein gravity you can be if you push the corrections to the Planck scale. Here we're going to be assuming that the corrections are due to some higher spin scale that's much less than Planck. And then we want to see how big can you make the corrections given that scale. Okay, so that could be in string theory, that would be the string scale, but we're not putting anything about string theory. Okay, so it's the other problem. And generally, if you write Lagrangian like this, in terms of the higher derivative correction, higher powers of Riemann curvature, we'll be trying to prove bounds on these coefficients. We want to see how big can they be. Okay? And we're going to be looking for things that scale in this way with the, as you would think from a derivative expansion of here. Yeah, we're going to try to show that these coefficients have to satisfy a derivative expansion in terms of that scale. So here's the setup. So I will spend a bit of time explaining exactly what we can bound and what we cannot bound. It's a very slippery territory there are millions of papers on modifications of gravity. I want to explain exactly what we do and what our inputs are, what are known results. And yeah, we'll go relatively quickly on the method at this point because it was reviewed in other talks, but I will stress what exactly what our minimal assumptions are. And hopefully in the end, I will flash some new results. So don't worry, I'm not going to try to talk about, to present 5 papers in the talk. But yeah, there's kind of a long series of papers that's going to be relevant there. And just notice that they kind of alternate between CFT and flat space. So it's been kind of fun in this project to input intuition from both. But mostly I will present results from about ongoing work. Okay. Okay. So we're going to be studying graviton scattering. That's as a way of probing gravity. Okay. So if we look at this particular amplitude, so with a specific, well, the graviton as a melicity, we're going to be looking at the amplitude that's not vanishing at 3 level. So that we're doing 4-dimensional gravity, to be clear. And the amplitude, importantly, at this factor in front. And then, well, there's Einstein's prediction. And then we're going to add a bunch of other stuff that are, for example, if you have correction, higher derivative correction at this vertex, you have a term like this. You can also have exchange of a massless scalar. And you can also have a bunch of contact interactions. And in this parameterization, the contact interactions are just polynomials. So they're very easy to list. Polynomials with some symmetry. And we imagining that this higher spin scale, that's going to be the REFT cutoff, is much less than the Planck scale. That allows us to neglect loops. This assumption of neglecting loops is often questioned, but I think for gravity, it's the most legit theory. It's the most legit situation where we can do this because loops are really suppressed by m over m Planck. Okay, so it's really a legitimate assumption. Okay. Let me have one slide just to explain what we don't bound. I'm not going to make a laundry list of what we don't bound, but just so we get an idea what we bound are. So, for example, f of r, people consider theories of gravity that have f of a function of polynomial in the Riemann curvature scalar instead of user Einstein. But this theory actually is equivalent, interestingly, to usual GR plus a scalar field with some potential. So actually, graviton scattering in this model is exactly the same as in the model we just talked about. So we're not going to give you any constraint on f. More generally, anything with a Ricci tensor or scalar, you can remove by field redefinition because Ricci tensor is the equation of motion of GR. So this thing has no imprint. So if I go back one slide, notice that two slides. Notice the thing we bound the radial powers of Riemann curvature. Okay, things that we can observe in the scattering amplitude. And similarly, we're not going to say anything of content about scalar potentials because they don't grow with energy. And yeah, always a lot of other modification of Einstein. From a perspective, they're just like adding extra matter or changing couplings to matter. So that's the way we think about the physics. So let me quickly review some known results. This matrix actually appeared in Brando's talk. So one argument for bounding this ioderative correction, it was observed that by these people called chems, that if you put ioderative correction at the vertex and ask whether graviton scattering against some object has a time delay with time advance, well, this question is really answered by an amplitude that's a 2x2 matrix, and the eigenvalues of that matrix give a time delay. And well, if you have an interesting thing is that the ioderative correction has different helicity structure, so it appears off the diagonal. So Einstein gravity always gives a time delay, is fine, but the correction, well, the eigenvalues of off diagonal matrix can be negative. So effectively, if you could trust this calculation in a regime where the off diagonal dominates, you will violate causality. So somehow if this term is present, the cutoff has to be low. And then these people argued that the cutoff has to be controlled by the mass of higher spin particles. That's what we expect. There's also a different line of argument using dispersion relations and forward limit, which are a bit dangerous, but we can try to apply them and see what we get. And if we apply forward, then generally what you do is you try to write couplings as integrals over something in the heavy sector, positive spectral density. When you can write some coupling as some positive integral, even though you don't know what happens in the UV, you know that if probabilities are positive in the UV, then the coupling will be positive. And this sort of thing that was being generalized to give two-sided bounds on various couplings by writing things as positive integrals. And somehow actually our approach will merge those two things. We'll be proving we'll be constraining vertices and contact interaction at the same time. Okay. And using just the graviton to scattering. Let me this is a slide about let's discuss some common complaints about the framework we use and why we're not going to worry about those. So one common complaint is that we're going to want to make bounds in 4D, and in 4 dimension, obviously, the S matrix does not exist because of infrared divergences. So I'm going to be talking about an object that does not exist. This doesn't worry me in the least because the reason it doesn't exist is basically because there's this divergent scattering phase. That's just because the Newton potential 1 over r doesn't die fast enough. And well, that's the part of physics we actually understand the best. So for me, it's hard to see how this could affect the short distance physics we're interested in constraining. And basically, for me, if you have a way of removing it, as David was suggested in the morning, you're just going to get better bounds. So right now, we're going to get bounds that have an infrared log in them. I'm happy with that. The other common complaint is that, well, why even talk about an S matrix? We live in an expanding universe and there's no S matrix. And well, in a way, you can try to quantify the effects, and like, for the same reason that we don't worry so much about curvature of the universe at the LHC, then this higher spin mass we think of as being much higher than the size of everyday objects. So I'm going to operate on the assumption that correction is expressed like that. If you want to constrain gravity during inflation and so on, that's a very interesting direction that people are currently pushing. I'm not going to be thinking about that setup. I'm imagining that this higher spin physics or stringy physics or whatever is happening at distances much shorter than the curvature universe. So effectively, I'm allowed to study basically flat space scattering. And yeah, there's also other issues with de Sitter space, like you cannot do an experiment with arbitrary high energy, but like I can't even conceptualize how this will matter, so I'm gonna ignore that. And if you have other complaints, you can drop them in the box at the entrance and someone will read them. Please do. And so before I go to the main part of the talk, let me also explain briefly why, as I stressed that our cutoff will be the mass of higher spin particles, let me explain why KK modes don't matter. So it's very natural to have light spin 2 particles. For example, if you have a Kaluza-Klein reduction at some large radius, but Kaluza-Klein modes don't easily decay into 2 gravitons. So in GR, for example, if you compute this 3-point vertex, each of these states is described by some wave function in the direction you compactified. But then when you integrate the product of 3 wave functions, you get 0 by orthogonality relations. So actually, there's no, the only way KK modes can decay is through higher derivative corrections at the vertex. So even if the Kaluza-Klein scale is much lighter than higher spin scale, we still expect that it's the higher spin scale which controls the corrections to GR. Okay, and that's this. So this is something we can anticipate, but doesn't matter. It's something we're going to see come out of our formulas. So spin 2 particles not matter. So the method that we use. So we studied 2-2-2 scattering. I'm just going to say a few general things about the kinematics, and basically to explain why the rigid limit is important. And the point is, if you think about fixed angle scattering, right? What might causality mean? You might imagine that causality means that if particles hit, if you do an experiment, you imagine particles collide at the point, then you don't get stuff coming out before a light cone that touch this point. But actually, this doesn't make sense. If you have objects that are extended objects, they will bounce and get there with a time advance at fixed angle. It's hard to make any argument at fixed angle. The thing that's where causality really is powerful is in the forward direction, because if you create some excitation at point 1 here, and you measure here in the forward direction, there's a real chance that point 3 becomes outside of the light cone of point 1. Outside the future light cone if there's time advance. Okay? Whereas at fixed angle, you're always in the future light cone of 1. Okay? So that's why the rigid limit, so forward scattering, is so important in this business. And the other important point to observe is that you might think that causality is about a particle coming from 1, not reaching 3 faster than light. It's not true. You can observe something at 3, even outside the light cone. But the thing is that the commutator will vanish. So what does that mean is that an amplitude from going from 1 to 3 has to exactly cancel an amplitude for an antiparticle coming from 3 to 1. So causality is not just a statement about particle, it's also a statement about antiparticles and crossing symmetry. Okay? That if you want to extract the full power of causality, you have to talk about antiparticles. Okay, so our assumption is our minimal assumptions. Physically, we assume that this scattering amplitude is causal and unitary at all scales, and is relativistically invariant at all scales. So what this gives us is analyticity of the scattering amplitude, and to be fully precise, we need an elasticity in the region of the following form. So we're going to be thinking about momentum transfer that are below the cutoff and energies that are above the cutoff. So we need an elasticity in that region here, basically outside this blue line. And if we have this elasticity region, then we're good. And we're also going to assume that it's bounded. The amplitude is bounded. As was stressed by David this morning, it's we're going to make an assumption that's a bit weaker than the usual one. We're not going to assume that. Usually, people assume that m over s squared goes to 0. Actually, I think it's, and this is a Froissart-like bound. This is actually hard to prove, but the bound we're going to use is weaker, but also much easier to prove. And the point is that we don't need the thing that's hard to prove in a Froissart bound is to control large impact parameters, and they're just not relevant for us. So we're going to imagine that we have the only thing that we're going to need are amplitudes integrated against wave packets that vanish at large impact parameters, and that finite support in momentum. And this mere amplitude, it's a very simple definition, but these mere amplitude have nice properties because it's a compact integral, they're obviously analytic in the full upper half plane, just like the amplitude was. But because they decay at large impact parameter, they're easy to bound. Okay, so they're bounded and analytic, and just from that we can prove dispersion relation for these mere things. So that's I think it's it's a nice conceptual development. So what does that give us? Give us some rules that relates these arcs, as Brendo was describing, which we compute from the low energy to physics at high energies. So we have some EFT stuff computed in terms of high energy stuff. And the only thing we're going to use about high energy is that it has a partial wave expansion. It's a sum of Jean polynomials. The Jean polynomials are oscillatory, but they show up with positive coefficients. That's all we're going to use. Okay. I'm going to describe some applications of this very quickly, so that I can go to the new stuff. So this actually I talked about last year at this conference. So as a warm-up, you can consider a scalar theory without gravity, and the simplest setup, if you assume that it's weakly coupled below the cutoff, but can be anything like. But causal is unitary above the cutoff. For example, you have a Lagrangian like this. I can map these parameters to a scalar amplitude like this. The first contact interaction 0 is dimension 8, and so on. And the goal would be to bound these higher derivative correction on the second line. And here I'm just going to say the results we found. So the result was proven by, let me come back, just taking these sum rules and expanding around the forward limit. And you get a whole bunch of sum rules, and actually you get some crossing symmetry constraints. Actually, some couplings can be measured by many sum rules. So if you have an optimization game where you can try to write a coupling as a positive sum of something, or minus a coupling as a positive sum of something, and by playing this game you can get upper and lower bounds on our couplings in terms of the smallest one, which is not written here. It's a quotient of d phi 4. So the subscript here is the number of Manastam, like s square. Yeah, G2 is quotient of s square, and so on. So, and what you find is that all of these couplings, all these higher derivative corrections, they satisfy two-sided bounds in either the cutoff and the leading corrections. And these bounds basically behave like a geometric series. So effectively, dimensional analysis is a theorem in this setup. And we can see a lot of things about this shape and some analytic results that I will not go into that. Okay. I want to move to gravity. A first step that we did last spring, that was to consider scalar where you allow graviton exchange. And now, when you look at this twice subtracted sum rule, dispersion relation, you find that in addition to all the contact interactions, there's a term that comes with that probes gravity. But this term has a pole, and obviously you cannot take a forward limit with momentum equals 0, it just blows up in your face. That's a well-known problem. And what we discussed last, and as David described a bit this morning, we can actually go around this setup. Instead of expanding around the forward limit, we cook up wave functions that we integrate over P with compact support and momentum. And again, we can use crossing symmetry to eliminate infinite series to rewrite these couplings as positive sums and effectively ignore those. And that way we prove the following types of bounds: that the horizontal axis here is the coefficient of del phi to the 4. And this is some vertical axis is higher derivative coupling. And now we have bounds that include gravity. So the allowed region is the inside of this triangle. We plot this for various dimensions. But our allowed region always look kind of the same as some triangle. And interestingly, the negative, the thing that used to be positive without gravity now can be slightly negative, which we believe is related to the fact that gravity is attractive and gives time delay, so the matter can give time advance. And yeah, so we found this type of bounds. In 4 dimensions, it's not on this plot. You get similar bounds, but with a log and for a divergent log, so it doesn't fit in the plot. And I could describe more the steps, but it turns out I won't have to do that because for graviton scattering, life would be easier. So I'm not going to describe the steps for scalar. I'm going to go directly to scalar. So some of the groundwork for graviton scattering was done this nice paper last spring, where they studied, for example, this is 2 interactions with a D4R4 type. There are 2 different interactions you can write down, and it's a bound on the ratio. And the solid line at the bottom is the region that they call prove is, well, if you're outside of that, it violates causality. And then the dots here show some example theories that are reasonable. And what strikes about this plot is the gap, like the difference between the theory space that's actually realized and the space that seems possible by these bounds. So I'm going to revisit this issue in a few slides. Okay, but it's very nice that the groundwork has been done for us. So I'm going to show some new results. So what we study, actually, everything I'm going to present here can be done just studying this MHV amplitude. And the important thing is that there's some spinor per factor times something that is polynomial for contact interactions. And this per factor grows like, energy to some huge power in some channel. And that means that if you do a fixed U dispersion relation, you get, right, the axiom is that M as M over energy square is bounded at high energy. M over T is bounded at large T. So that means that this function here vanishes at large T. So we get some rules like this, fixed U dispersion relations that converge without anything in the denominator. This is called superconvergence, and as you see, it's awesome. So what is it? Okay, before I describe how it's awesome, I was just going to describe something. Oh, I think I'm missing a slide. Sorry, about so this superconvergence relation basically is going to measure gravity and nothing else. That's why it's going to be useful. Before we use it, we can also play the game of looking at more subtractions and try to bound the contact terms. And we've played this game, essentially the same game as was played in the in this paper, but we played it a bit differently. Instead, we plotted the things differently. We look at ratios of coupling. So this is D4R4, and A00 is R4 interaction. And when we plot these ratios, the size is a bit crowded, but when you plot these ratios, you find something interesting about the exclusion plot. So the dashed lines here are the thing that was plotted before is the ratio of these 2 quantities, A21 over A20. And so that's a slope here. And you see that at fixed number of orders, so the different regions are for different derivative order, basically. A different derivative order, you see that the exclusion plot becomes tangent to the slope at the origin. So if you put, for example, this one here, 7 derivative, if you ask what's the bound on the ratio of these 2 couplings, A20 over A21, what's the minimum slope, then, well, it looks like it's mostly 0, but when you zoom near the origin, you find this curve. And if you zoom by another factor of 100, you will discover that the orange curve becomes tangent to this dashed line near the origin. So kind of amazingly, the lower bound on the ratio was always minus 90/11, no matter how many derivatives you take. But when you look at this exclusion plot, you see the bigger picture that actually this A21 here just can't be negative. So the actual lower bound, we believe, is 0, not that. Okay. And similarly, the upper bound, even though there's a small region here that's tangent, the actual for the bulk of the region, it's much yeah, the ratio on the slope is much less. Here we end up with 2.3 instead of 6. Okay. So we believe in most of the region that's realized, basically except from a infinitesimal region near the origin, we believe that the actual region is between the 0 and this 2.3. And we're not claiming that the allowed region that we now have is populated by Terry space. Maybe it can still get smaller, but I think we definitely shrunk the discrepancy between Terry space and the bounds. So that was just essentially by accounting for this phenomenon that, yeah, when you look at the exclusion at the different couplings and you have a bit more inequalities, when you look at the story of essentially you only exclude negative A21 asymptotically, but it's clear that yeah, the more functionals you use, the more closer to 0 your bound get. Effectively, it's dangerous to look near a cusp and look at the slope near a cusp. It's dangerous. Okay. So let's go back to gravity, the main thing we're interested in. How much time do I have?
You have, well, 5 minutes, including questions. So if you can wrap it up.
Oh, okay, yes. Okay, I'm basically done. So I'm going to show one more plot and make some comments. So with gravity, the thing that's great is that when you look at this spin 2 sum rule, I call it spin 2. You use the word spin, not subtraction, because there's no subtraction, but it means that it converges marginally on spin 2 exchange. It probes gravity. And it proves a finite number. It basically proves these contact interactions. It proves nothing else. It doesn't, sorry, it's either the vertex correction doesn't prove contact interaction. So this is a finite sum on the left. And you can write it because some OPE on the right. And the important thing is that that thing we're actually going to do with this is much easier than what CMZ did. We're just going to try to find, you can take this equation and integrate against P in order to get a formula that proves that G is positive. That sounds boring. We know the gravity is attractive, but once you have a sum rule that's positive and that proves that G is positive, you can use that sum rule to dominate every single other coupling in the theory. So everything is bounded by gravity. So we get that sort of exclusion plots that look like this. So G4 is the coefficient of R to the 4, and G3 is the coefficient of Riemann to the cube. And I'm dividing, there are units of a factor of Planck units in front of this. So I'm expecting these things to be some power of the cutoff scale M. The important thing is that we're bounding, when you write the Lagrangian in this form on the right, we're bounding these coefficients to be order 1. Like here on the horizontal axis, it's 10, 10. So that's an allowed region. So in other words, you cannot, if you have you cannot have this thing turned on without having a higher spin particle in your theory. And that has to be a higher spin particle that couples with gravitational strength. It cannot be a multi-particle state. Okay. So let me just say what does that mean in short? Well, what do we know about higher spin couplings? Well, if you have a higher spin particle that couples gravitationally to matter, we'll have seen it. Okay, like very conservatively at LHC, we produce processes like this with missing energy. And the basic reason we have seen it is that this higher spin particles, they grow like crazy with energy. So if even though there's a Planck suppression in this, it's hard to imagine that anything less than EMeV you wouldn't have seen. And if there are couplings here that make this thing softer by exchanging other stringy particles here, then like we would have seen that as well. So So the synology should be analyzed carefully, but it's extremely hard to imagine that this aeroderivative scale is less than, very conservatively, tiny fraction of a meter. Okay, so what does that mean? Conclusion. Well, the way we're thinking about this is that, suppose one of these experiments about precision experiments about GR were to disagree from GR by more than 10 to the minus 40, the size of the object in units of 10 minus 13 meter. Then there are a bunch of explanations that one could try. Maybe there's some new scalars. This is constrained by other experiments. Maybe there's some kind of conventional new physics or new particles. This is what we're ruling out. So that leaves two other options. Well, maybe experimental error, or maybe causality doesn't work the way we think it does, which is possible. But we're ruling out basically in any kind of new physics, because new physics would have to come with a spin-4 particle, and there's just no hint that this is there. We'll have seen that if it was the explanation. Okay, so we have some open questions. Really, the next thing to do clearly is to bound couplings to matter, control loops. We believe that by going slightly away from forward limits and so on, we control loops, but that's to check. Yeah, that's it. Thank you.
Thank you very much, Simon. So there is a hand raised by Sasha. The robot has announced it.
Hi, Simon. So when we observed that the shrinking and we looked under the hood, we found that shrinking occurs in not one, but infinitely many plots due to this hierarchy at the level of partial waves. So I wanted to ask, if you look not at this plot, you show this cusp behavior. Can you tell us what happens for a broader set of couplings?
Oh, you mean the ones with more and more derivatives?
Yes.
Yeah, I don't really look, but I would think that if this one wing shrink by a factor of 4, the next one should shrink by a factor of 16, and so on. But,
well, this was quite special, in fact, and yeah, so it would be interesting to see.
Okay, yeah, we should look. I don't have plots really.
Thank you.
Thank you.
Any more questions for Simon? Yeah. Yes, Andrew.
Hi, can you hear me?
Yes.
Okay. Yes. So I just wanted to ask, because you're assuming you're doing this kind of a weakly coupled thing where you're ignoring loops and thinking of corrections coming from higher spin. Yeah. But obviously loops from ordinary, standard model particles, whatever, give contributions Riemann cube, Riemann 4 as well to different scale. So could you just comment on that?
Yeah. So on the scale of this plot, if you have a loop of one heavy particle, it's you're gonna have an effect that goes like 1 over Planck to the 4, right? Because it's G Newton square. So in this plot, it's like at the origin. So a loop of one loop ordinary matter is very close to origin, unless you have a very large n number of matter particles. But then this plot is basically telling you that you cannot have n bigger than m Planck square over m square.
Right. So
so you only see the loop effects only show up on the same plot here if there's a large n number of them.
So I'm a bit confused, but obviously that's true for, understand that from the gravity loops, but from, ordinary,
well, we still have
parameterization. So for example, the Riemann cube. So if you integrate that massive loop, the mass scale would be, you'd have m to the 6 of the loop would be m to the 4 times m Planck squared in your, no, it's the other way around.
Exactly, yeah.
Whichever way it is, yes.
Yeah, there's an extra suppression by m Planck square, yeah.
Yeah, there's an extra suppression, but when you're running these arguments, the cutoff, the scale in terms in the dispersion integral should be set by the mass of the loop you've integrated out, right? It's not the mass of the higher spin mass.
Yeah, this is so the way we think about it is that, I mean, if you have loops, there's one assumption that we haven't proven, and that's sort of the next thing to show, is that the coupling of gravity to matter cannot exceed like usual expected strength. That follows kind of the slogan we're seeing here, that all the couplings are bounded by G Newton. So if matter cannot couple to doesn't have unexpected couplings to gravity, then the matter loop would be proportional to 1 over n Planck to the 4th, and that makes it negligible on this plot.
Yeah, although sometimes, I mean, you know, light mass particles, their loops, even though they're n Planck squared suppressed, can still actually make a comparable contribution.
Well, the other thing
to-
that we have to discuss is that some of, for example, some of the functionals used in this plot evaluate things close to forward limit. So if you have something like 1 over m Planck 4, but that goes like 1 over t, the thing is you never get behavior as in the forward limit that's more singular than 1 over t, up 2 logs. And so as long as 1 over m Planck to the 4th times 1 over t is negligible in the regime that we work, I think that light loops don't matter.
Maybe we can move this discussion. We leave the Zoom room open, but we have the people who